Thank you, Robin. Thank you, Susanna. It's a pleasure to be here. And as I was looking through the program, right, a lot of EI is now centered around AI. So it's really, AI is revolutionizing so many areas. And what I want to focus today is to ask how it can make a deep impact in scientific domains. So if you think about how we solve problems in, say, various scientific workflows, right, you limit to a set of like hypotheses, you go do experiments, and then you come back, you revise the hypothesis. That's the scientific method. And still, most of it is done in physical labs. You go, you set up a wet lab experiment, you set up a telescope, so it's all done physically. And in an ideal world, we would be able to build digital twins, and we would be able to simulate all this to high accuracy or high enough accuracy so that you get a really good sense in the digital twin, in our virtual worlds before we go do those physical experiments. This way we can explore a lot better, right? A much larger design space, much larger set of hypotheses. And so that's the question, how do we get there? How do we make these scientific simulations much more accurate? And what class of AI models are effective in that? And that's where neural operators are a new class of methods that give you the broad notion and requirements of what kind of AI algorithms we would need here. Yeah, so with that overview, let's dive right in. So where do these problems arise? Almost everywhere, right? So one of the hardest problems today is how do we tackle climate change and how do we accurately forecast and predict climate change. And the challenge for this is it's not just based on historical data. You also want to predict for the future. And today that's done with numerical methods, solving very refined turbulence equations of the cloud, and that would give you the most accurate predictions of the future. And to do that, the biggest source of uncertainty today is in terms of being able to model these what we call stratocumulus or low-lying clouds. So how do we model that effectively? And that requires extremely fine resolution. So 1 meter spatial resolution globally, right? And that's what creates the expenditure for numerical methods. So you have to go to really fine grids and run them also over time. In fact, you want this at 1 meter and 1 second grid points and keep going for 100 years. I mean, this is way too expensive. In fact, it is so expensive that even with accounting for the current computational growth, which we know is plateauing, you would only be able to do this in 2060 because it needs about 100 billion times more computing than what we have today, even with all our greatest and biggest supercomputers. And so just to give you an idea of a moonshot, right? I mean, we really need this. The planet needs this. But we are limited by compute. And we know the equations, we know the physics, right? I can write this down. But how do I actually resolve this? How do I come up with numerical solutions is extremely slow. And if you look at the partial differential equation solvers, you're doing this from scratch over and over again. Every time you change a parameter, you have to redo it again. But on the other hand, AI has a potential here because it learns from a lot of examples, right? It learns from many families of equations potentially. And so that way it could do much faster. And it doesn't need to work on the native grid. You don't need to go, essentially, it's not necessary to work on a spatial resolution of a certain, say, 1 meter, because neural networks and other neural architectures we know do nonlinear transformations. So there could be a different latent space in which you don't need that fine grid. And so that's where we see a huge potential of machine learning substantially speeding up these kinds of methods. And not just the potential, also evidence in many of the scenarios. And this is the slide our CEO, Jensen Huang, likes to always talk about, right? The end of Moore's law, single-threaded computing plateauing, and we need accelerated computing like GPUs. And they've really revolutionized just, every area where computing is needed, as you can see. And then on top of it, we need the scale up and out. Our supercomputers are now coming to the exascale era. And as Robin mentioned, even HPC for imaging is a big deal. HPC for science is a big deal. HPC for COVID-19, I'll talk some of the results we did for COVID-19, given the immediacy of some of the research needed there. So all that needs supercomputing. Our supercomputers are getting to exascale. They're getting much more integrated CPU, GPU systems, right? And they're also getting to mixed precision. So when I say exascale, it's for what we call the AI flops or the mixed precision flops, right? Which is also another big advantage. So these numerical methods not only require fine spatial and temporal grids, they also require extremely high precision. Sometimes 64 floating point, or even 128 for some methods. On the other hand, we can get away with mixed precision for so many of the AI workloads. And so all this will really help us, right? And that's why that is the cherry on top is machine learning. So we need machine learning to take us all the way to making these methods actually feasible. Because all of this adding up, right, the machine learning itself, if we see in many applications, give us as much as 1 million times speed up, hundreds of thousands to 1 million times speed up. And so that is the one that's going to take us all the way. But we need to build it on the foundation of GPUs and other accelerated computing. We need to build it on the foundation of all the supercomputing and high-performance computing. We need all of that foundation. And on top of it, if we run the right AI algorithms, we can create magic. And that's what we are on a mission to do. So let me tell you now what neural operators are and what is the special class of Fourier neural operators, and why are they so relevant to partial differential equations and other scientific problems. So the main property that these methods will have that standard neural networks do not is the notion what I call discretization invariance. The ability to handle different resolutions of your input. The ability to predict at different resolutions and give you outputs. Right? So, for instance, if I trained any of your favorite neural networks, right? Could be convolutional neural networks, transformers. In general, if you train it on one resolution, so all your training data is at one fixed resolution, you can't just feed in an image of a different resolution. Right? So the generalization would be quite poor, and many times it won't even take that as an input. That's not a valid input because it's just designed for a certain training grid. But that's not how numerical methods work. If I want to run partial differential equations or other scientific simulations, other simulations in general, people like to choose different grids, right? If it's an airfoil, you want to choose an irregular grid, for instance, because certain points here, like this corner, is really important to go have a very refined computation there. And so, it may not even be a uniform grid. And even if it's a uniform grid, you may want to refine it. Mesh refinement is a big aspect of numerical methods. And so we can't ignore all of this and say, oh, you're not going to have any of this. Your only choice is to limit to one resolution. And even if, let's say, the scientists agreed with that, the problem is you may not capture the fine scales given only one resolution, right? Because the model, standard neural network generalization theory, what does it tell you? Right? It tells you that you will generalize well at that resolution. There is no guarantee it will capture finer scales than what it is trained on. There is no guarantee of zero-shot super resolution. So zero shot because you haven't seen finer resolution data at training time, right? And you want to be able to do that at test time. So how well can we do that? How can we enable this? Otherwise, to me, there is no hope of completely replacing numerical methods. And that's what many of the early attempts have been in this area. It's like, let's start with a numerical method, and then deep learning gets you to a high resolution. But there you're assuming that your low resolution input is again on fixed training grid. The output is another fixed training grid. It's a start, but again, it doesn't take us all the way. And more importantly, it doesn't give us all the speed ups if you're still going back into the solver in the loop all the time. And even just infrastructure-wise, I know a lot of teams are trying to build those. They're not so easy, right? So because all the engineering, first of all, you would have to bring that to the GPU. Many numerical methods are not completely there, right? And if they're on the CPU, that communication will kill you. So all these aspects make it very hard. And indeed, what we are asking is ambitious. We are asking, can we just replace these numerical methods, right? Not just augment them. And is there a fundamental principle in which that is possible? And so what that would entail is you're not just limited to a discrete grid of points as input or discrete grid of points on which you compute the output, the solution, but a function space. So if you think of your input as a function, so the function takes location, right? So you can query anywhere in this continuous domain, not just on those grid points. So your input is a function, output is a function. Can I learn the mapping between that? And that mapping we call the operator, right? That's the operator theory. So you're generalizing from discrete inputs and discrete outputs of a fixed size to where the input is a function itself. And that function you can query at any location in your domain. And that's usually a continuous domain. And so that's where we want to generalize. And and we solve with, now to conceptualize, let's start with the simplest setting, the linear operators. For instance, linear partial differential equations. One popular example is the heat diffusion, right? So, if you have uniform heat diffusion, you can see the heat, if it's hot here in the boundary, it eventually diffuses, right, and becomes uniform. And so you can think of equations like this, where we know it's linear. And in this case, we know, in fact, what the closed form solution looks like. Because of linearity, if the input is a function, let's say v of y, that could be giving you the initial and boundary condition of the problem. Let's say in this case, the initial condition. And then after integrating with a certain kernel, which is the Green's function, if you've seen PDE 101, right? That's the function over which you integrate that kind of tells you how uniform or non-uniform this domain is, and how does this diffusion change based on your location, right? And also pairwise, it's a pairwise function. And so that one, if you integrate with, that mapping is what gives you the output, which is the solution. So this is a general structure for any linear partial differential equation. I start with an input, right, that is a function. So now it's no longer, you could discretize this. You could just say, now y is on some discrete set of location. This integration becomes just summation. But if you want to do this without one discretization, be able to handle multiple discretizations of different levels, we want to be learning an approximation to this continuous integration. So you could do that in two steps. You could learn the kernel, you could learn this function k, and then or kappa, and then integrate over that, or you could directly try to learn this integration. So ultimately, by creating an approximation to this computation, you can then go and query at a new point, right? And it could be outside the discretization you used for your training data. And so that's the concept here. But it only applies for linear partial differential equations. And in the case of a partial differential equation, we know the inverse of differential operator is the integral operator, right? And we know because it's linear, it is this integral linear operator. And that's why it's this form. So we know the form, but it's only linear. And sure, there have been many attempts to try and learn the kernel or try and learn some form of discretization of this integration, but it's only linear, right? So that's a limited class of PDEs we can solve with that. And so now the question is, can we take this concept and extend this to any general nonlinear operator, any general nonlinear partial differential equations family? And that is the neural operator. And it's conceptually very simple. What we are saying is, come up with ways to approximate this integral linear operator and then compose it with certain nonlinearity. Could be nonlinear activations like rectified linear units or GALOOP, right, the Gaussian or other kind of which have the higher order derivatives, which are preferable here, but I'll come to that later. But conceptually, you can take a nonlinear activation and compose your linear operator. And if you do that over more than one layer, you can get universal approximation. And that's how, in fact, a proof for even neural networks works, right? In a neural network, your block here is a linear function. Matrix multiplication, convolution, they're all linear functions. And then you apply some nonlinearity on top of that. That means now you can learn the basis functions. And that's how you can approximate any function in fixed dimensions through that. So the same concept, right? So far, I'm not giving you a practical implementation, but just conceptually, what would be a universal approximator? Some set of operations that can give you a good approximation of linear integral operators, and then compose that with nonlinearity. And so once you do that, we can approximate any general nonlinear operators. And then we can learn this end-to-end. We learn both the blocks that compute the integral linear operator along with this nonlinear composition. So everything is very similar to neural networks. Now the only question is, how do we compute these integral linear operators efficiently? Of course, the first cut is what I already mentioned, right? You could discretize this and come up with a way to estimate kernel. And once you have the kernel, you can, again, provide an approximation of the integration even at other locations other than your training data. But the challenge with that usually is that and those are what we call graph neural operator. They're like graph neural networks, except you can derive the kernel and apply it even on new nodes that were not in training data. And we did that, and they give good results in certain domains like molecules. I'll tell you about that. But for domains like fluid dynamics, they tend to be very expensive, right? So if you directly discretize, and especially as the dimensionality increases, you go from 2D to even 3D, for instance, this becomes pretty hard to do. And so what we will do instead is to do directly an approximation to this integration by change of domain. And so we'll think of a special case within the kernels, which are convolutions. And because we're composing it with nonlinearity, you can still keep the universal approximation result. That's a small detail there. But the interesting question now is, once it's convolution, how can we compute convolutions efficiently? Can go to the frequency domain, right? And that's what we do here. Convolution becomes multiplication, element-wise multiplication in the frequency domain. And then I can do inverse Fourier transform, and I come back to my standard domain. And so that's how we can do this now efficiently, right? We know fast Fourier transforms are very fast. They take only quasi-linear time, and then we can also do the inverse. And so it just means we are learning now weights in the frequency domain. So I'm just learning how to change my weights at different frequencies, right? I'm multiplying my input frequency, intensities with now the learned weights. And indeed, these methods are very popular, right? Pseudospectral methods are the backbone of numerical methods, and that's where we also got the inspiration. But the difference is we are not just doing a linear approximation here. The difference is we are going to learn this and compose it with nonlinearity, right? So I should have had the new figure, but anyway. Yeah, so this is very simple. So I'm just showing a block of doing the Fourier transform, learning the weights, and doing the inverse Fourier transform. And as an additional regularization, we can retain only low-frequency modes. So this is more of architectural and regularization question. It turns out that this really helps well in generalization. It helps well, in terms of being able to learn, also in terms of the optimization angle. But yeah, the algorithm is very simple. We are doing now I have it. The fast Fourier transform, learning weights in the frequency domain, doing the inverse, doing nonlinear activations, and composing them over several layers. And this results in being discretization invariant, because you can do Fourier transform on any domain, right? Of course, implementation-wise, what is the right one? That depends. If it's uniform domain, we know it's fast Fourier transform. And we have an extension for non-uniform grids. You can first learn a deformation to a latent grid that is uniform, so you still retain the computational speed. But this is the architecture, very simple, right? So you have now the processing done in frequency domain, but we are not just doing it once. We are coming back to the standard domain, doing nonlinear transformations, and doing this again and again. And so this flexibility of nonlinear transform with the efficiency of spectral processing is what really makes a difference in so many domains. And the other difference is if you think about convolutional neural networks, those convolutions are done only locally. They're small receptive field. And for many domains like fluid dynamics, they all have very global correlations. So they can't capture that. And that's where many attempts have been made to use UNets and other convolutional models. And they do well if you give a fine enough initial solution, and then it refines it, because then it's only local information. But if you give it no information, it's all global correlations, right? If you ask it to solve from scratch, and it doesn't work well. And that's the other benefit with the frequency domain, right? It has global correlations being captured well. Because if you recall the uncertainty theorem, which is a detail anyway. But that's the idea, this is fast, this is efficient, this is universal approximator. And so the notion that I mentioned of discretization invariance, just to kind of hone in the point, the idea is once you train a model like this, right? I mean, this is an airfoil, it's non-uniform grid, but it applies to uniform or non-uniform grids. You should be able to refine it and be able to evaluate the model at any resolution. And not just that, its approximation should be good, right? It should be able to, as you refine the grid, it should converge to a limit that is a good approximation of the underlying operator. And that's where, these are more details, but what it says is neural operators satisfy all the nice properties here. For instance, a nice baseline is you can train a transformer or unit at a fixed resolution of training, and then just do standard interpolation on top, right? Both for input and output, you can say bilinear or whatever your favorite interpolation is. But that one will not give you a good fidelity. The error could be quite large, especially at the higher resolution on which you haven't trained. And so that also, this is kind of formally saying that it's not a universal approximator. And so that's the benefit here, that now we have expressive models that have the ability to approximate operators, right, which are mappings between function spaces. And once you've trained them to a good point, because they have the approximation result, you have to, of course, train them well, right? But once you've trained, you can query it at any point in the continuous domain. So that's the concept. And now the question is, what have these achieved? I'll give you some range of examples and, what is the impact there. Just as a starting one, this is a simple fluid flow, just, 2D, right? But to show you the concept, we trained it only on low resolution data, and now you can see that we're able to evaluate it in the higher resolution. And of course, there are numerical plots in the paper, but the idea is, you can now get good results even at higher resolutions than what you trained on. Yeah, there are some additional details of how to optimize this well, because as I said, one of the hyperparameters is how many modes do you retain at different layers, right? So by keeping only the low frequency modes, the good property is you can generalize better, because higher frequencies can become more overfitted to one resolution, right? That's a challenge always. And it also leads to more stable training. But on the other hand, it can underfit. If you have too few modes, you don't get a good approximation of the underlying operator. And we've come up with also good, efficient training algorithms where you incrementally increase both the resolution of your training data and the number of parameters in your model, or the number of modes you retain after the Fourier transform. And so that's the idea, that you can kind of progressively train. And this is very true with a lot of other computer vision settings too. But there, the notion of what is an easy example and then a hard example, like a curriculum, is hard to derive. But here it's straightforward, right? Because coarser resolution data we know is easier to first approximate, right? The coarser scales, and then you can go to finer scales. And so we can again use all the notions from physics to make our training more efficient, and it generalizes better. And so far this is completely data-driven, right? So the idea is some solver gives you now a set of training data of solving partial differential equations or other simulations, and then you take that and you can train the neural operator. But on the other hand, if I limit it or no data, what do I do? Right? And that's the physics-informed setting. We have the equations, right? So by physics, I mean we have the equation constraints. We can use that. And so we can combine the two. This field really started with the physics-informed neural networks, or PIN, right? The difference from PIN to neural operators is in PIN, there's no data, right? And there's one instance of PDE. So you're given a fixed initial or boundary condition, you want to solve it. And the optimization landscape becomes quite challenging, and you get stuck, especially for, let's say, dynamic flows or anything dynamic, right? Because the optimization landscape is too hard. On the other hand, instead of trying to solve one instance of the problem with the PINO setting, with the physics-informed neural operator, we want to learn the operator itself. So we're going to try and solve multiple instances of the problem. And so the idea is, I'm giving now input with multiple initial and boundary conditions. And if I have data, so if I have data from a solver, I can use the data loss. So saying this is the standard data-driven setting that we talked about before. So optionally, if I don't have data or some limited amount of data, I'm going to add now my physics constraints, my loss from how good are the equations satisfied. And then I can combine both of this. And there's also a nice efficient way to do this, compute the derivatives in the Fourier domain. The full field, you can get derivatives very efficiently. That's a detail, but an important one for efficiency. But through that, you can now come up with a better model because you're incorporating physics, right? So even if your data is limited, or your data is in a coarse, but like you don't have all the fine resolution data. You have data at a fixed resolution as training. You can now add the physics losses in the finer resolution. And that's another great benefit of this method, by the way. You could now feed in data at different resolutions. You can also feed in physics constraints at different resolutions and points. So you have a lot of flexibility to choose that well. And by doing that, we see that we can do well. As an additional detail, if let's say you do all this training, you learn the operator, you're not happy with the result on one specific instance. I train my neural operator, and then I ask it to solve for a fixed initial condition. But you can check the solution. You can see, is this good or not? And that's another great benefit, by the way, compared to other settings, right? Here you can check the solution. We can tell you, is it satisfying the solution or equation or not? And so you can further fine-tune to do it better. And we see this setting also really being able to further drive down the error, and because you already start with a good initial point, even if it's not the best error. The other benefit is you can do transfer learning. So this is Reynolds number 100, this is 500, right? I mean, if it just like do it data-driven, you may still get some error, right? But with incorporating the PDE, the equation, it's a much better transfer learning setup because you know what changes from one distribution to another. And that's how we see that you can do transfer learning much more efficiently because you have data from one setting and now you've changed the setting through changing parameters in your equation. You can also do inverse problems much more effectively with these physics-informed neural operators. By the way, that's a great benefit of all these methods, right? You're speeding up neural operators of the forward simulation. Then you can do inverse problems as well very fast. And with incorporating physics losses, you can do that even better. Yeah, so that was an overview of the methods themselves. Now I'll quickly go over some of the results and how effective they've been. So this is called ForecastNet that uses Fourier neural operator operations. And what we see here, I mean, these are the atmospheric rivers that are really hitting us. Right? I mean, not this exact one, but this is the phenomena, right? These are thousands of miles wide, and they bring all the rain that we are seeing here. And so predicting them well is really important. As you see, the orange versus the blue, there's a very good correspondence. And not just this, from all the metrics as well, we can show that we can do as well as the numerical weather models for as much as 2 weeks, right? 2 weeks further, we can forecast very accurately while being about 45,000 times faster. And so in this case, we did it completely data-driven. We threw away all the physics, but we have tons of historical weather data. And so that's, in fact, open source, right? You can go and download this. And our model is also open source, by the way. It's ForecastNet with 4, as in Fourier. If you look up, you can go and download. And so this is the first open source, very high fidelity weather model. Right? And it's very fast. You can run this on a single GPU in a matter of few seconds, whereas it would take many hours on a CPU cluster for standard numerical weather models. And it can also predict extreme weather events. For some reason, that video is not working, but it's online. And we're also building on Omniverse very interactive tools where you can set up and create how many ensembles you want, what kind of visualization. Here it's a hurricane. The pink is more the variance, right? So you can visualize all this in terms of how that is evolving. Yeah, so just an overview of how we're able to capture much finer scales. Our AI model is able to capture 25-kilometer resolution, right? This is the finest resolution open weather data that is available. And through that, be able to get really high accurate results. And this is just the first step, right? We can couple models of digital twins of all sorts of things. For instance, the weather model can inform like a model of wind turbine or power plant, right? And then it can help us plan the electricity grid, especially when there's chance of extreme weather events, right? Planning for the grid is so important. So it's hugely important to be able to do accurate weather prediction, and that's what these techniques enable. We're also able to do carbon capture and storage, which for climate change mitigation is a big aspect. How do we pump carbon dioxide, store it deep underground? How does it interact with water? And what is the based on the permeability of the subsurface that we know, how well can we model the pressure buildup and the gas plume? So let's say I give you a picture like this. I tell you this is how the permeability looks like, right? And this is known from various surveys. And these are the wells where I store carbon dioxide. We can, once I tell you this, we can use our Fourier neural operator models and come up with a prediction of how these gas plumes will grow over 30 years, right? So very long time interval, but you need that. You need to know how the pressure buildup will happen. Is it safe for me to store carbon dioxide underground? And this is 700,000 times faster. So in fact, we did this as a multi-grid approach where it's fine grid around and inside the wells because you need very refined simulation here, as you can see, right? This is highly nonlinear evolution of the gas plume. But away from the wells, you can have coarser grid. But they're still permeable, so there's still some dependency, so you need to model that. And so by doing all these efficient techniques, you can come up with very fast speed-ups here, which I think you can now go and explore this on all your known wells, right, and select the best one. You can do that for ultrasound wave propagation. And we are doing this, for lung ultrasound with a collaborator. We have also done that for capturing molecular dynamics, so how the conformational changes occur as the coronavirus replicates inside a cell. And this is some more detail on that, but this paper was a finalist for Gordon Bell Prize for large-scale HPC computing for COVID-19 in 2021. And the goal was to build a bridge between cryo-EM, or experimental data, right, which is very familiar for all of you in imaging, and the AIMD is the all-atomic molecular dynamic simulation, right? So highly accurate simulations here, but how does it match with experimental data? And we can use machine learning surrogates to do that. And that's where our methods, gave a lot of good speed up there. We can also do that for computational lithography, where the modeling problem is, given like a mask image, what is the final resist image, right, that would appear on the wafer, the silicon wafer? And the inverse problem is mask optimization, because you know what should appear on the silicon wafer, what is really my starting mask to get me what I need in the end output. And usually these are very expensive to do with standard simulation tools there on CPU. And the inverse problem is hard because, right, you come up with some mask image example, it's not the wafer you want after your simulation. So you go back again, you twiddle. There's no nice computational framework to do that. And so we used neural operators, and we also added some convolution as a side chain or another parallel network, because it's just, it can quickly capture the local correlations, and then the more global one, the Fourier neural operator does, which is a detail. And we can do full chip simulation. We also need to add some padding for aliasing effects, which is a detail of Fourier transform. But if we do all that, we can do much better than UNets, for instance, and we can capture the forward simulation very effectively. But to me, the even more exciting aspect is to do inverse lithography, right, or the mask optimization. So the key here is we get impressive speed up, 600 times speed up. But more than that, you even get better mask quality than what you would do with numerical solvers. Because in this case, you can do progressive self-training, meaning you come up with good candidates of mask quality, you further train on that and you refine. And so that's the benefit of a data-driven approach. You're not limited to one fixed solver. You can keep getting better and better. And so it's like, right, and this we've seen with computer vision too, right? All the self-training there, so you come up with pseudo-labels, you train on those, you get better. So similar concepts here, but with Fourier neural operators. And so you can get good speed up and better mask quality. And I think for inverse design, inverse problems is where the benefit is even more compounded, because it's not just about speed up, it's coming up with better candidates than was possible before. So in the last part, I quickly want to tell you about how all this connects to implicit networks and radiance fields, right? So this is very popular and has really revolutionized 3D rendering, and going from like traditional rendering to now neural network-based rendering, right? And this is where implicit representations now can represent the ability to generate any view, right? So these novel view synthesis is a big aspect of it. And so these continuous representations you could think as a special case of neural operators under the general lens, because it's also mapping from one continuous input, which could be the location, angle, right, viewpoint angle, and so on, to the output, which would be the color, right, at those locations. And so that's also continuous representation. And so that's a connection that many may not immediately realize. But there's, of course, special inductive biases for rendering that is used in many of the state-of-the-art NERF models. And so, what I wanted to tell you about our take on this in a project, what we call perception, was to ask, can we use this representation not just to synthesize novel views, not just to render, which is what community has been doing very well, but also can we use it for downstream perception tasks directly, and will that improve performance? So having an implicit representation of my data instead of just the RGB, right, pixels, is that a better input to do perception and other downstream tasks? And so that was our question, and that's where we created the largest scale per radiance field data sets. So it's both scenes and objects. This is open source. I encourage you to go check it out. And this is called perception. So it's perception, but with radiance fields. And so with this, what we hope to ask and hope for people to further explore is that can these implicit representations not only give you viewpoints, not only help you with rendering, but help you with solving all kinds of downstream perception tasks, right, like segmentation. And so that's where the idea is, it's not one task, it's lots of tasks, right? You can do all kinds of 2D classification, segmentation, all your favorite two-dimensional image tasks, but also three-dimensional image tasks. You can classify objects and shapes, and you can also do segmentation. And so the question is, will these representation help? And the answer is yes. From our study, what we see is having this implicit representation gives you more of the 3D information, right? So for 2D tasks, it helps you have a better information and hence better robustness. And I think that's also a nice question and a connection we are exploring. What is the role like neural operators and implicit representations played together? And neural operators, we have made a choice with Fourier transforms and certain architectures, right? And in this case, the planoxels, the spherical harmonic coefficients are just very similar, right? They're essentially Fourier transform, but on the sphere. And so there's a lot of nice geometric structure built into both. And these are just linear representations, but neural operators are nonlinear, right? So there's a question of can we make this also much more general for implicit representations? So So yeah, to conclude, I hope I gave you a foundation of what neural operators are, why they're necessary, right, and how they generalize neural networks to learning operators, which are mappings between function spaces. So that means you can query anywhere in the continuous domain outside of your training data. You can go to higher resolution than what your training data was available with. And you can now impose physics losses like partial differential equation penalties on higher resolution than your training data. And so all that now gives us the ability to replace numerical methods and get orders of magnitude speed up, hundreds of thousands of times, right? Sometimes tens of thousands of times, but also be able to do inverse problems very effectively. Like we saw with inverse lithography, you can do progressive self-training and all kinds of design optimization and get better than what numerical solvers have been able to do while being faster. And I think that's where there's a lot of exciting possibilities of what these methods can do. And I'd love to hear from your domains and your interests where this could be applicable. Thank you.